Welcome back. We're still doing thermal practice here, and this is one of the more complicated questions that we could ask using the heat lost equals heat gain sort of idea. We've got a mystery fuel, and we burn some of it, and using the heat, we warm up a glass cup and some liquid inside it. And then they ask us what the enthalpy of combustion for the fuel was. So there are two things going on here. We have the fuel burn, which is a chemical reaction, so we'd use E equals N delta H to figure out how much heat comes out of it. And on the other side, we have the material warming up. There are two things warming up here, and they're each going to use energy equals mc delta T. For the glass, they say there's 150 grams of it. The specific heat for glass, they tell us, is 0.84. And our temperature change, we went from 10 up to 45, so a 35-degree change. 45 degrees is kind of tepid hot chocolate, but all right. And 150 times 0.84 times 35 degrees. It took 4,410 joules of energy to warm up the glass. I say joules because I gave this mass in grams. That means the specific heat would be in joules per gram degree Celsius, and so our energy comes out in joules. If you wanted to work in kilo units, you could put 0.15 here for the specific heat of the glass cup. This would still be 0.84, but it would be kilojoules per kilogram. And then this answer would come out as 4.410 kilojoules. So both ways work. So this is the amount for the glass, and also we heated up some liquid, and they tell us there was 500 grams of that. Specific heat, you could guess 4.19 for hot chocolate, but maybe it was made with milk or something. It's got a lower specific heat. 3.75. And the temperature change is the same. When liquid's in a container, they almost always end up at the same temperature. It's very hard for that to not happen unless it's a thermos or something. They're touching over so much surface area that they kind of have to end up in thermal equilibrium. 65,625 is what I find for the heat absorbed by the hot chocolate. Add those up. 5, 1 plus 2 is 3, 4 plus 6 is 10, carry a 1, 4 plus 5 plus 1 is 10, carry a 1. 70,035 joules, or 70.035 kilojoules, is the energy that went into heating stuff up. Now that we have that energy, we can go over to the other side, and for the fuel, we can say, we know you released 70.035 kilojoules because we just found it over in these materials. So our total energy here is, or enthalpy, is 70.035 kJ equals number of moles. Almost always here you end up doing some molar mass thing to find N, but in this question they were nice and they just told us it's 2.34 grams. Or sorry, moles. I guess they couldn't have us do the molar mass thing because we don't know what the fuel is, so they were kind of stuck doing this. And we are being asked to find the delta H, the heat of combustion. So to solve this, divide both sides by 2.34, and we get 70.035 kilojoules divided by 2.34, 29.929 kilojoules per mole is our enthalpy of combustion. Even though I started the question in joules, I kind of quietly switched over to kilojoules here just because delta H's for chemical reactions are almost always given in kilojoules per mole. A joule is just such a small amount that it gives you awkwardly big numbers. So if you found 29,929 joules per mole, great, you're also correct. Last thing, let's think about significant digits for a second. How many should we have here? 3 in our moles. The masses had 3, delta T had 3, specific heats had 3. Did I use anything that didn't have 3? I know these delta T's look like 2 significant digits, but that's me being lazy about the final digit. Really, if you do 45.0 minus 10.0, the difference is 35.0. So 3 sig digs there too if we're accurate about it. So it looks like we're good to give 3 sig digs in our answer, and so we would say 29.9 kilojoules per mole. And if you gave that as your answer, it would be technically wrong. Do you see why? Is this reaction endothermic or exothermic? It's exothermic, and so technically this number should have a negative on it. If they had said how much energy is released or anything like that, then we would be kind of off the hook. It would be understood that this number is a negative, but since they didn't, you should be on top of it and specify that it's a negative. How do we know this reaction is exothermic? Because the surroundings heated up. The glass cup and the hot chocolate got warmer. That only happens when you have something like a fire that's throwing heat. If these things had gotten cold, that would mean our reaction's sucking heat out of the surroundings and we would be thinking endo, but today this is exo.